Good afternoon, madam. I am Ms. Jahnavi from CSC second year. AA assignment 2. Today my topic is half adder and full adder. So let us first look at my topic, that is introduction to binary adders, and we will look at the overview of the half adder and full adder, and then we'll go to the block and circuit diagram of these half and full adders, and to know the truth table and K-map simplification for these. And at the final, we get to know the applications and the conclusions. Dive into our topic. But before going to our topic, let me tell you what is a binary adder. So a binary adder is a combinational circuit that performs addition of binary digits and bits. That means we all know a combinational circuit. A combinational circuit basically gives outputs based on the present input only, but not on the previous output. So binary adder is an example of combinational circuit, and depending on the design and configuration, we have two types in this binary adder, that is half adder and full adder. So let us first look at the half adder and then go to the full adder. So first we have half adder. So the basic definition of half adder is that it is a combinational logic circuit with the two inputs and two outputs. So we all know, as I mentioned above, what is a combinational logic circuit. So this half adder is a combinational logic circuit, and basically a half adder is a circuit which has two inputs and two outputs. Let us assume that the inputs as A and B, and we always get the output as sum and carry. So when we look at what is sum is the result of adding A and B, and the carry, it is a value that indicates if there is an overflow in the addition. Next, let's look at the block better. So first we have the block diagram. So here we basically have two inputs, that is A and B, and then we have two outputs, sum and carry. When we look at the circuit diagram, here we can see the which gate we have used. For output sum, we have used the XOR gate, and for output carry, we have used the AND gate. So let us look at the truth table. Basically here in the truth table we can see that the inputs A and B, to give the output sum, it performs XOR operation since it is a XOR gate, and to get the output C, it performs AND operation. Let me a brief introduction, that is truth table of half adder. See, here we have that input and output. Input is A and B, and the outputs are sum and carry. So basically we take this 0 0 0 1 1 0 and 1 1 as inputs, and here we have the output sum. For sum, output 1 is only when the inputs are different. So this is basically represents the XOR gate. In XOR gate, always the input is 1 only when the outputs are different. So now let's look at the carry. So here carry is output 1 only when both the inputs are 1. So this is the property of AND operation. So this sum and carry basically performs the logic gates and or XOR operations that has represented here. So K-map simplification for half adder. So here when we look, I have given the K-map simplification for sum and for carry. Since we all know that what is the K-map simplification, let us look at the equation that we have obtained, that is S equals to A bar B plus AB bar. So this is the equation that we have acquired by the K-map simplification. And when we look at the carry, we have also an equation that is A dot B. Here a dot is missing, sorry for the mistake. Now let us applications of half adder. So the half adder is used in arithmetic logic unit, and it is also used in calculators and to calculate addresses and tables, and it is also used to realize full adder circuit. So these are the basic applications of half adder. Now up to now we have discussed about what is an half adder and the block diagram and the K-map simplification and the applications. Now, what is a full adder? So a full adder is designed to overcome the drawback of half adder which is the ability to add only 2 bits. So let me mention one more important thing, that is half adder has the main drawback that it can only add 2 inputs. So this is considered as a drawback, and to overcome this we have the full adder. And this full adder basically has 3 inputs and 2 outputs, and it is a combinational circuit. Now when we talk about 3 inputs, among 3 inputs we have 2 inputs as A and B, and 1 input it is a carry from the previous output. And the outputs will be the same, that is sum and carry. Basically sum is the result of adding 3 inputs, and the carry out, here since there is 2 carries, that is from previous and the present, we represent the previous carry as previous carry, and the present output carry as carry out, and it is value that indicates if there is an overflow from the addition, which is passed to the next stage. Now let's and circuit diagram to get a better understanding. So here we have the block diagram, which represents 3 inputs and 2 outputs. Here we have A, B, C that has inputs and sum and carry as output. Now when we look at the circuit diagram, we have the 3 inputs normally as the block diagram, and for the output sum we have XOR gate, and for the output carry we have 3 AND gates connected to an OR gate. So let us look at the operation of this in the truth table of full adder. Here we have input and output. Inputs are 3, and here basically let me tell you a small cheat code to write this truth table. We get 4, 2, 1. That means at A take 4 and B 2 and C 1, and then just go on adding the zeros and ones in the order from 0 to 7. And in the output, when we look at the sum, here we get sum as 1 only when the outputs are different. Same to the half adder, here also that XOR operation is used. In XOR operation, we all know that zeros, the output will be 1 only when the inputs are 0 and 1. That means both are different. So similarly to the half adder, there is here the sum is calculated. And when we look at the carry, we all know that carry has AND operation, and since the carry output will be 1 only when we have both or 3 inputs as 1. If you look at the 4th row, we have 1 1, then we get carry as 1, and when we look at the last row, we have 3 ones and the carry as 1, which means the carry output will be 1 when the inputs both 1 or 3 1. So this is all about the truth table. Look at the K-map simplification of full adder. So I have presented for sum and for carry the K-map simplification. And this generally K-map simplification, how we write, we all know. So this sum and carry equations we are obtained through the simplifications. Let me read out the equation for you. S equals to A bar B bar C plus A B bar C plus A bar B C bar, and finally we have A B C, and the carry equation is AB plus AC plus BC. Now this is the K-map simplification. So these equations are basically, we have obtained these equations through the rules of binary addition and K-map simplification. The applications of full adder, basically there is more applications to full adder than half adder. I have given many here. Let me give few for you. Like full adders are used in arithmetic logic units, calculators, to generate memory addresses, and carrying out multiplication of binary numbers, and many more. Up to now, we have discussed what is a full adder, block diagram, circuit diagram, and K-map simplification, and the applications of full adder and half adder. So let us just revise what we have learned up to now. In the conclusion, we have half adders are basic arithmetic circuits used to add 2 binary digits but cannot handle carry from previous stage. So this is the main drawback of the half adder, as I explained before. So to overcome this, we have took a new thing, that is full adder, and these full adders are used like allowing us to take the previous output carry to the present output. Now let us see that we have covered the essential concepts of full adders which are crucial in digital electronics. Full adders are vital as they help implement various other important digital circuits. So half adders and full adders, or up to now we have discussed, and finally thank you very much for listening.